The embryonic development of liver is closely connected with the development of the pancreas. If this would be the embryonic stomach and the future duodenum, then here ventrally we got a hepatic butt, the primordium of the liver. Another butt is the gallbladder primordium and the ventral pancreatic butt. On the opposite side, dorsally, we got dorsal pancreatic butt growing dorsally. And here will be the rest of the duodenum. So let's use some colors to differentiate all these butts and diverticula. Purple for the hepatic butt, green for the primordium of the gallbladder, and blue for the ventral pancreatic primordium, and let's see, yellow for the dorsal primordium of pancreas. These butts are infiltrating the ventral mesentery, the ventral mesenteries here, and the dorsal mesenteries. So if this is the stomach, here is the ventral mesentery, the dorsal mesentery, then this is the dorsal pancreatic butt, this will be the ventral pancreatic butt, this is the duodenum, this will be the primordium of the gallbladder, and this is the liver butt, or hepatic butt, the primordium of the liver. As all these butts are growing and proliferating, we got a different situation here. After some time, this will be the upper part of the duodenum with a dorsal pancreatic butt, and here is the ventral pancreatic butt, the cystic duct with the gallbladder, and then the common hepatic duct branching into the right and left hepatic ducts. And from these ducts, the endodermal epithelium is proliferating into that ventral mesenchyma, and these cells will become the hepatocytes. These endodermal cells will become the parenchyma of the liver, the epithelial component of liver. At the same time, the blood vessels that are here in the ventral mesenteries, and that's actually the vitelline vein, becomes divided by the growth of this hepatic cords, and this will become the system of the liver sinusoids, and the mesenchyma here will become the liver mesenchyma, and all the mesenchyma derived cells of the liver. So that's how the embryonic components, these are the embryonic components of the liver tissue that originates here. I will add the colors for the dorsal pancreas, the ventral pancreas, the ventral pancreatic butt. The liver is already purple, and the gallbladder will remain green. So if this is the dorsal pancreatic primordium, the ventral, pancreatic, primordium, the gallbladder, this is already the cystic duct, and this will be the common hepatic duct, and this will be the right and left, and left hepatic ducts. All of these epithelia being of endodermal origin because it's derived from the gastrointestinal tube. Now this is proliferation of the hepatic cords. Hepatic cords are proliferating into the mesenchyma, of the ventral mesentery, and their proliferation will divide the vitelline vein into the system of hepatic sinusoids. So if we proceed to the histological level, then you would realize that the classical liver morphological lobule with the central vein in the center, the hepatic cords here, in 1 to 2 rows, anastomosing and dividing only in a simplified manner here. We got the hepatic sinusoids with their highly permeable wall inside. The hepatic sinusoids are carrying the blood towards the central vein. So that's how the histological structure of the liver emerges. And here we got the portal triad. In the portal space, that's where we got a branch of the hepatic artery proper, a branch of the portal vein, and a hepatic, bile duct with simple cuboidal epithelium, together being called the portal triad. And here, everywhere are these triads. So we understand that even this connective tissue here originates from the mesenchyma of the ventral mesenteries. So these are the hepatic cords. Hepatic cords, or cords of hepatocytes, the liver sinusoids. So these hepatic sinusoids are these vascular spaces that carry the blood from the portal veins and hepatic arteries into the central vein. Here is the portal triad. And the connective tissue. So now we understand the embryonic origin of this histological structure of liver. Let's go back to these organs. Now the important point is the ventral pancreas will rotate here behind the duodenum towards the dorsal pancreas to join it. So after this rotation, we got the duodenum here, the original dorsal pancreas with its duct, and now also the ventral pancreas together with the choledochus duct. That goes behind the duodenum. Here is the cystic duct, the common hepatic duct, and the right and left hepatic duct with the liver, etc. So this is the gallbladder, the dorsal pancreas, and the formerly ventral pancreas. The bile duct, the dorsal pancreas, the ventral pancreas, gallbladder, and the bile duct here. The rest is the same as the common hepatic and right and left hepatic ducts. So this is the outcome of this rotation. Finally, we could explain the most common situation when we got here the duodenal window, and here is the duct of the ventral pancreas, which will drain not only the former ventral pancreas, but in most cases it will also drain the dorsal pancreas. It will kind of kidnap the drainage here. The opening here into the duodenal wall is together with the ductus choledochus, but in some cases we got an additional accessory pancreatic duct as the persisting duct of the dorsal pancreas. And here is the choledochus bile duct, which goes behind the duodenum like this. So let me at the borders of the final pancreas, these two parts will merge. So that's why we have the head here, the uncinate process, the pancreatic incisure, and here the head of the pancreas, the body, and the tail. The upper part of the head and the tail originating from the dorsal pancreas, and the uncinate process and the lower part of the head originating from the ventral pancreas. So this is the choledochus, bile duct, which in most cases opens together with the major pancreatic duct, on the major duodenal papilla. Actually, when there is only one duct, it doesn't make sense to call it major. It's normally, in most cases, it's just one pancreatic duct. It's also called duct of Versung. But in some cases, there might be this persisting accessory pancreatic duct. Of Santorini, that is present in some approximately 10% of individuals. When present, then it opens on the minor duodenal papilla, which in the adults is like 2 centimeters cranially to the major papilla. A reason why we explain all this is to explain the immense anatomical variability that is here in the opening of the Cleidocus duct and the pancreatic and the system of pancreatic ducts. There's a plethora of types and subtypes and openings. These two could open together, being like absorbed by the growing wall of the duodenum, or they can open each individually, being completely separated, etc. So many options resulting from that developmental mechanism. Now the endodermal tissue of the pancreas will differentiate into 2 types: the exocrine pancreatic tissue with the serous acini, so I'll add some pyramidal shaped serous cells with the round shaped nuclei, and the basophilic cytoplasm due to the rough endoplasmic reticulum and the zymogenous granules storing the proenzymes of the exocrine pancreas, and the centroacinal cells of the first ducts, etc. And the other cells of the same origin will differentiate into these endocrine islets made of trabecular epithelium with a complicated 3-dimensional structure. These are the endocrine islets with the capillaries or sinusoids inside. So just to remind you of the fact that we got both exocrine serous acini in the pancreas, as well as the endocrine pancreatic islets of Langerhans. With the blood sinusoids here. So this is the duodenum, right? Otherwise, I hope the scheme makes sense to you.